Hello, everybody. So today we're going to be talking about, on a very heuristic level, Einstein's field equations of general relativity, and in particular, how curvature is relevant in these equations. Okay, so we'll start with a brief overview of Einstein's field equations. These are set on a particular space. The formal definition of this is a differentiable manifold, so we'll go through this at a very heuristic level. On this differentiable manifold, we'll be able to do geometry. So I'll talk about an overview of how curvature works in differential geometry more generally, and then we'll circle back to the Einstein's field equations, where I'll discuss the particular combination of curvature terms which enter there, as well as the relationship to local energy conservation in general relativity. Okay, so this is just what the Einstein's field equations of general relativity look like. This is just schematic at this point, but what I would like you to keep in mind is that on the left-hand side, there is stuff related to the curvature. We're going to go through this more precisely in the video. And on the right-hand side, there's stuff related to the stress energy. That's the stress energy tensor TAB, which may be familiar from the context of Maxwell's equations of electrodynamics, for instance. So the basic structure is this curvature is going to be a function of the fundamental object for us, which is what's called a Lorentzian signature metric. So that's going to be GAB. And the energy could also be a function of this metric. So this will turn out to be a very complicated partial differential equation for the metric components, right? So I would like to draw a little bit of a parallel to Maxwell's equations of electrodynamics, where similarly we have a field, so the electric and magnetic fields, and in that context, those are thought of as being sourced by charges and currents, right? So you set some differential equations for the field equal to quantities involving the charge and the currents. So in a sense, this is somewhat similar to that. However, the subtlety which is appearing here is that the energy terms, which are functioning analogously to the charge and current of electrodynamics, themselves could be a function of the metric. So that's entering on both sides of the equation where you're solving for the metric. Uh, Whereas for Maxwell's electrodynamics, these are essentially just prescribed functions, right? But sort of schematically, this is a somewhat similar picture. And this is very much motivated by essentially the classical gravitational perspective of starting with Poisson's equation, right? Okay, so now we're going to go through very heuristically how we model a notion of space in general relativity. And mathematically speaking, this is the concept of a differentiable manifold. So typically what we deal with is something like Rn, and then we can talk about functions and whatnot on Rn. And the basic idea here of what a differentiable manifold is that we have a space that is covered by sets that structurally look like Rn, right? So the space doesn't on a global level look like Rn, but locally in a sense it does, right? And these are what are called coordinate systems. So for each of these, at this very heuristic level, you could just think that we have some particular coordinate system in the sense that you're probably used to dealing with just computations on Rn associated with each of these open sets. So that's what computations look like locally on a differentiable manifold. Right, so then we have all of these charts which cover the space, but what happens if they overlap? And that's where the smooth part of a differentiable manifold comes in. So there's a precise sense in which if the charts overlap, a certain composition of the coordinate charts essentially must be smooth. All of this can be made much more rigorous, of course. This is just supposed to be very schematic. But the key point related to differentiable manifolds, which is relevant for when we do geometry, is that you can show that each point on an n-dimensional manifold has an associated n-dimensional vector space, TPM, associated to it. And this is what's called the tangent space at a point of the differentiable manifold, right? So this is a vector at a point. You could define essentially a vector field over the whole manifold, right, by just considering vectors at each point, but you want that to be smooth in a certain sense. So that essentially could be characterized locally in terms of one of these charts as the coefficient functions being smooth in the typical sense, right? But really, the key point for us is that you can just define this vector space at a point, and that's what we'll be using to do geometry, right? And again, all of this can be made more formal. So as we denoted earlier, the fundamental quantity which we're interested in the context of general relativity is what's called a metric. So this is a symmetric two tensor. So in particular, it's going to be multilinear. And what's a little bit different from how you usually talk about in mathematics, for instance, differential geometry, is that the signature of the metric tensor used in general relativity is kind of different. So the signature is going to be essentially the number of positive, negative, or zero eigenvalues at a point. We would do this in a particular basis, but this is a basis independent concept. Um, so typically in differential geometry, you use what's called a Riemannian signature metric. So you're going to have all positive eigenvalues. But in general relativity, you have what's called a Lorentzian signature metric. So I guess depending on your convention, it would be a minus eigenvalue in, say, the time direction, or yeah, the time, yeah, and essentially the time direction locally, and then three positive eigenvalues, right? This is somewhat a matter of convention, but the point is they're not all the same sign, and there's going to be one that has a different sign. So this is the Lorentzian signature metric. Okay, now we're going to iterate up starting from the metric and develop all these notions of curvature, which are uh, really can be thought of as very complicated functions of the metric and its derivative. So the first step in doing that is to introduce this quantity called the Levi-Civita connection. So a connection more general, there's a more general concept of a connection, and this has to do with the first part. Uh, so for an affine connection, it will take two vectors as vector fields and the manifold as arguments, give you a new vector field. It will behave with a specific way with regards to functions applied to the x and y arguments. This is just all typical for some kind of connection, but Levi-Civita is special because it's what's called metric compatible and torsion free, right? So this derivative of the metric should be zero. That's the metric compatible part. And the torsion free part is the derivative in the x direction of the y vector field minus the derivative in the y direction of the x vector field is related to what's called the Lie bracket of the two vector fields, right? So really at a heuristic level, this is just a quantity that's determined by the metric, right? For the sake of this video. And in particular, we can characterize this connection in terms of what are called Christoffel symbols locally. This has to do with how certain basis vectors are affected under the derivative transformation. These expressions are at the bottom. So really, just for the sake of this video, we'll mostly be using the Christoffel symbols doing things locally, in particular coordinate system. So you can think about this as a function of the metric, basically. Okay, so starting from the Levi-Civita connection, now we move on to this notion of Riemann curvature. So this is actually a genuine tensor, and this is going to take three vector fields and give a new vector field, given in terms of this essentially Levi-Civita connection, right, in the following sense. So we can characterize this locally in terms of the Christoffel symbols using the bottom expression. And in particular, you also get certain identities associated with this curvature tensor called the first and second Bianchi identities, which constrain certain components. They are certainly not all independent. Even in the four-dimensional case, there are going to be a very large number of components of this tensor. Okay, so as I said, not all the components are independent. You can characterize quite a bit of information in the Riemann curvature by just tracing over the first and third indices, and this is what's called the Ricci curvature. So this is going to take two vector fields as arguments, right? It's just the trace as such using the metric. But yes, it is not encapsulating as much information as the Riemann curvature. But we can actually go even farther and trace the Ricci curvature again, and then we get the scalar curvature. So this is just going to be a function. So just as an aside, we've introduced these three notions of curvature, the Riemann curvature, the Ricci curvature, and the scalar curvature. And these all correspond to different levels of information. The Riemann curvature encapsulates quite a bit. There are a lot of components of this thing. Ricci curvature is still a strong condition, but it's certainly weaker than Riemann. And then scalar curvature is actually a very weak condition, right? But it's not a nothing condition. But why I'm saying this is that the broader study of differential geometry makes quite a bit of point of studying the relationship between certain curvature conditions, so conditions you can impose on different notions of curvature and how they relate to other quantities in geometry. What sort of constraints this puts, say, on even the underlying manifold at the level of its structure. And this is a very interesting area and is active research in differential geometry. Right. So now we've introduced all of the curvature ingredients, and what we do is we consider this particular combination of the curvature. So the Ricci curvature minus 1/2 the scalar curvature times the metric, and this is what's called the Einstein tensor, and this is the left-hand side of the Einstein field equations, assuming there is no cosmological constant. Okay, so a natural question is why do we take this particular combination of the curvatures and have this appear in the Einstein field equations? uh, if we start from the premise that we want to equate some notion of curvature to some notion of stress energy, the stress energy takes a particular form, so our curvature thing should have the right number of indices. But there's a more compelling reason than this. It's that we expect there should be local energy conservation in general relativity. And what this means is that this divergence of the stress energy tensor should be necessarily zero, right? So in order to enforce that, we would want a particular combination of the curvature tensors such that this is the case. And this happens to be the case for the Einstein tensor itself. So if we equate that up to some constant with the stress energy, that will enforce local energy conservation. Now, there's a variety of arguments you can use to motivate the structure of the Einstein field equation, including this such argument, but ultimately it comes down to experimental tests. That's really the decisive factor as to why the Einstein field equation has the form that it does. Okay, so I think I'll call it there. I'll be making some more videos on various aspects of geometry and physics. So stay tuned, and thanks for listening.